the book that that he put out a while back. I believe 28, 29 years experience in process engineering and plastics, scientific molding, all that good stuff, and a master's in plastics engineering from UMass Lowell. We've had quite a few from that university, and obviously a really well known program. So we kind of always go back to that water hole, and we're always learning from those folks. So I think with that, Suhas, I'll maybe I'll hand it to Weston real quick actually to talk about Q&A, and then we'll get started. So thanks again, everybody.
Yeah, thanks, Bennett, very much. Great to have you back, Suhas. Real quickly here, we'll allow Suhas to present his stuff here and hold the questions and answers to the end. You can always submit them throughout the presentation and at the end of it through the Q&A section located on the lower right-hand corner of your screen there. Direct any questions or comments to the host. They'll come in here to myself, and then I'll read them off once Suhas is done. So I guess with that, let's turn it over to the man of the hour. Suhas, it's all yours, bud.
Thank you. Thank you. So first of all, thank you, Howard Bennett, and also to Sodick to give me this opportunity to talk to you guys. I think this is a very interesting topic that I'm going to talk to you guys. A lot of times, and I'll tell you, so just to give you guys my background, I know some of you all have attended the last webinar that we did here, and some of you all may have attended my other talks. But just to give you my introduction, yes, I have been doing this for about 28, 29 years. I started off, I finished my master's in plastics engineering from UMass Lowell. And then I really, for some reason, I really liked injection molding. I was so passionate about that. I really liked the technology. So even after my master's, the first thing I did is I took up an internship position because that position was with Rubbermaid, and that, you know, I was able to go and work on the machines and learn something there, right, on the machines. I wanted to be hands-on. And even after that, the first job I took, because when I was an intern student, I was not allowed to touch anything, so as to speak. I mean, the screens, yes, but I was not able to do like a mold change or anything that way for safety reasons. But the first 2 years after that, I worked at the Scott's Corporation. You may have seen the fertilizer spreaders, the green Scott's fertilizer spreaders. That is to be molded right here in San Diego, and it's now just literally moved about 40 miles north of here in Temecula, California. And I started there as a technician on the production floor, right? So I was changing molds and working there, doing maintenance and so on, right? So I did a lot of hands-on stuff, and that's what has really helped me learn more stuff. And I've been like that throughout. Then I started working at MIE, and I read, this is now 1995, pre-internet days, right? For the young guys in the room today, you probably can't even fathom what it is without an internet, right? So we read books and magazines, and I started reading about scientific molding. I never took any course in injection molding. I started just reading all this stuff, and then I realized that there's a lot of these things that is very, very confusing. It's not complicated, right? You just have to understand the basic concepts. Once you understand the basic concepts, I think you come up with these things. So I started doing that. And I started finding out that, you know, yes, this is what it is. And then slowly, and every single time I do a seminar, I teach. Right now, I'm in the middle of a seminar right now. Today's the last day of a 6-day class. It's online, 4 hours a day. Today's the last day. I just literally learned something new a day first when I was running the machine, right? When I say that, so it's always, my mind is always working. So back pressure, even I was not setting back pressure correctly. What was I doing? Set it about, we still have hydraulic machines that I set it about 60 to 70 PSI, 80 PSI, that's fine, that's it. But then I started realizing, you have to understand what these things are and how to set it. Why is that? It's because you have to come with a good, robust process in the end, right? So let's go through this. There are actually 3 important reasons why you need to understand back pressure and how to set it, right? So we'll go through each of these things here. So the injection molding cycle, if you look at the injection molding cycle, right, there is the, 1 second here, let me just, yeah. So there is the injection phase. After the injection phase, you're filling the cavity with molten plastic. Then you go into the what I call as a compensation phase. So it's which consists of the packing phase and the holding phase. In a lot of cases, you can have only one phase, and they call it as a holding phase. Okay, that's perfectly acceptable. But sometimes you have to separate them into two and call this a packing phase and the holding phase. Like I said, I call this a compensation phase. Once this is done, so what are you doing? Why do I call it compensation? Because you're compensating for the shrinkage that's taking place inside the mold when the plastic is cooling down after the injection, right? So this is the first phase. So once you do this stuff, then you have to go into recover the screw. That means the screw has to go back to the short size, and at the same time the plastic is cooling down, right? Then the mold open, injection, mold close. So this is your basic injection molding cycle, which is a very simple concept out there, right? There are what I call as 11 plus 2 injection molding parameters on the machine. Okay, in no particular order of importance, it is the cooling time, the pack and hold pressures, the pack and hold times, the melt temperatures, injection pressure, injection speed, the back pressure, screw rotation speed, short size, transfer, and the mold temperature, right? So I say 11 plus 2, I don't say 13. Why is that? Is because if you do not split pack and hold into two, you have 11. If you do end up splitting them, then you'll have 13, right? When do you split them? A great example is if you've got a hot runner system, right? Or if you've got a very large gate, right? In that case, you'll have to have a pack and hold in there, right? So these are the inputs. By the way, I'm pretty sure somebody's trying to take a screenshot of this stuff. Don't worry about taking screenshots and all that stuff. I'll send this to you for free. Okay. So it's a nice high-res picture. I'll send it to you. Right, what you need, just let me know. I'll be more than happy to send it to you. If you my only request is if you use it, please give me credit for that. Right. So these are the inputs, and then these are the outputs. So here's the other thing. Like I said, please don't use it and not give me. So here's somebody, they took my stuff and they just went and changed this into Spanish, and the guy put it up on Facebook. So please don't do this. With just respect, I spend a lot of time working on these things, guys, right? So I'll be happy to give it to you. Just put my name and use it. You don't have to pay me a single cent or anything that way. Okay, thank you. So now let's understand, right? Let's go to back to the back pressure. So what do we do? What are we trying to do always when we're doing a mold qualification or coming to the molding process? You're setting the molding process so that the parts that you make are going to be very consistent, right? That's what you're trying to do, right? So you have to ultimately reduce all the variations, right? Variation, where does it come from? Variation can come from all these molding parameters, all these 11 plus 2 molding parameters. You'll get variation from. So what is your job? If you want to reduce the variation in the final molded product, then you need to make sure that you reduce in each of these 11 plus 2 parameters is what you want to reduce the variation by, right? So you cannot get rid of variation. Variation will always be present, right? You just need to know how to minimize it. And that's one thing I've done over the years. I've developed some of these techniques, and some of these techniques are not my techniques, of course. For example, viscosity curve, the people from RJG teacher, John Bozelli, they came up with these things. Of course, I borrowed that, but there's a lot of other stuff. If you go through my class, it's a 4-day class. You go through, you'll see that there's something, especially design of experiments, right? That is my huge, big area into injection molding. So I have come up with these things. In fact, the one I'm going to show you today is also something that I came up about, say, 7-8 years ago, and I've started formalizing that and teaching it. So my goal is to optimize and reduce the variation in each of these 11 plus 2 molding parameters, right? That's when you'll be able to now reduce the variation in your molded product, right? Where do you get your the current source, right? Of 1 second here, I'm trying to hide a panel. Manage panels, I guess. Yeah, please let me remove some of these things because I cannot see my own presentation here. Okay, there you go. Right. So where do you typically get your information for the settings? Yeah. See, you will typically go to the data sheet. When you go to the data sheet, it says this is a manufacturing data sheet. This is for an ABS material. It's a very, I won't mention the name of the company that manufactures it, but it's a very, very popular company. But see, this data is not correct data. Okay, a lot of people will look at this. Hey, it says right now, it says that you need to set back pressures from 43.5. I do not know. Has anybody ever set 43.5 PSI, right? You don't get decimals over there if you're using PSI, right? We know this, right? What do? They simply take this, somebody does that, they've got an intern in-house, he takes that and just converts 0.300 MPa into PSI and puts that number here, right? That is not correct. That's not good data. This is not, you have to know, you have to learn to make data-driven decisions in injection molding, right? So this is absolutely not correct. Good guideline, but that's not how you set it, right? And 202 PSI. In fact, all these other things too, percentage shot size, we know that for those of us who are in molding, we know that we want to stay between about 20 to 80 PSI or 20 to 70 PSI. And sometimes you can even go below 20 PSI and it's perfectly okay. There are exceptions to that. But 50 to 70% of the barrel, absolutely, that's not the right thing to do. You're going to be buying a molding machine for every single mold out there. Of course, the people at Sodick are going to be very happy about it, but that's not the right way to do it, right? Vent depths. I have done some studies on vent depths. Look at this vent depth. It's 0.00201. Can you show me a machinist who can machine that to that accuracy, right? So screw speeds. I talk about screw speeds here. RPMs, right? RPMs is not thing. So again, please do not take this as the Bible and say, hey, this is the molding Bible, and therefore this is what the suppliers are telling, and that's what I'm going to use it, right? So that's not the right way to do it. So don't blindly use data sheets. Also, data sheets, when they give you, it's very misleading in other ways too, right? Look at this, right? It says fabrication conditions for injection molding. Of course, they use this stuff. It says barrel temperature, chilled water. Cycle time is 200 seconds. I don't know which company is going to be in business if they run a mold for 200 seconds. And this is a very large part, of course. Yes, but we don't work. And then they're defining fill times, defining holding times, right? And then typical value is not to consider specifications. User should confirm their own result. So what I'm getting to is that, guys, for your back pressure values or any values, do not use the data sheets blindly, right? Be very careful when you look at the data sheets, and also educate your customers who are not in the molding business, right? Educate customers that there's a lot of mistakes in these things. Yeah. I hope that there's somebody in the materials suppliers is listening to this talk, and then they go make those changes in there, right? So again, I'm very big on basics. So I'm going to tell you basics, a few things here. There's something called the PVT diagram. This plays a huge role in back pressure. So I want to tell you this, right? What's a PVT diagram? PVT diagram is, it simply means that if you take any plastic and you start increasing the temperature, the volume increases. Okay, so here it is at atmospheric pressure, 0 MPa. The volume keeps on increasing as you start increasing the temperature of the plastic. But now plastic melt is compressible. It's like a big ball of rubber band. So you can actually compress the same amount of plastic, and when you compress it at that temperature, what's going to happen is the volume is going to reduce. That's exactly what we do in injection molding, right? You melt the plastic in the molding barrel, and at high pressures, you inject it inside the mold. And when you inject inside the mold, because the mold is cold, it starts to cool down, and now the volume also reduces. So you're basically getting a combination of this PVT diagram inside your mold, right? And that's the whole idea of using pressure sensors that's supplied by RJG or Kistler, right? What they do is that if you get the same pressure, volume, temperature at a given time inside the mold, that means now you have got the same quality of part, right? That means you've got the same amount of molecules, and therefore your density stays the same, and therefore you're going to get the same dimensions. Okay, so keep this in mind, right? Again, this is a basic thing. Okay, how does it play a role in back pressure? You'll see that very soon here. So this is your PVT diagram. Screw recovery speeds is related to, of course, because we're talking about screw and back pressure, all that stuff. Always make sure that you're measuring your screw recovery speeds not in RPMs, but always in circumferential speeds. Okay, why is that? Because see, if you have got a large vehicle like this and a small vehicle like this, 1 RPM of the small, or from 1 revolution of a small tire is going to go a shorter distance compared to a 1 revolution of a larger vehicle, right? So what happens is you have 2 screws, same RPMs, one is going to have a low shear, other is going to have a higher shear. Right? That plays a role in your melt temperatures because you're giving shear energy to the plastic. Okay, so that's to do with screw recovery speeds. Now, what's back pressure? Yeah. So if you visualize yourself, going down a slope, right? You're going down a slope like this with this load, or you're running down a slope. You're going, Saturday morning, you decide to go for a run and it's a big slope, a down slope. What do you tend to do? You tend to apply a force that is opposite to the direction of travel. You're traveling here, but you put some force in opposite in this direction. Why? Because you want to control the rate at which you take this load down the slope, right? If you don't do that, what's going to happen? You're going to go crash and you're going to go fall down. So what do? You apply that force. So the same thing happens in injection molding. In injection molding, as the screw is turning, okay, there is some amount of pressure that's applied at the back of the screw so that now you're bringing that screw back consistently, especially at, let's say, high screw speeds. Okay, so first thing is that there may be some people who are new into injection molding out here. The way this works is that during injection, so let's just say that the shot has been built up. During injection, this screw acts like a plunger. Okay, there is no function of the back of the screw out here. Right? The flights is useless. During injection, it's only a plunger, so just moving it straight. Right, there's no turning taking place. Once the plastic is injected inside the mold, then the screw starts to turn. When the screw starts to turn, it acts like an auger, right? This is like an auger, right? So the plastic now it gets conveyed in the front and now it comes and settles in front of the screw. There is nothing pulling the screw back. Okay, there's nothing pulling the screw back. As the plastic comes and sits in front of the screw, as it collects here, it now pushes the screw back here. Okay, so that's how this works. Now, if I don't put this some pressure here, what happens is that the screw can just turn erratically and basically it can just come and make the short size. What the short size is where you start the injection of the plastic, right? It can come in and hit, especially like I said, at high screw speeds, right? So you're gonna have a bounce. If you think of it, there's going to be some bouncing taking place. It's going to come and hit your short size, and what happens? The amount of plastic that is in front of the screw then is not going to be the same every single shot. So what you do is that you have to put some amount of pressure at the back. Of course, we'll define how much to put, so that you can consistently bring the screw back. That's the first thing that you need to do. Then there are three zones on the screw, right? There is the feed zone, there is a transition zone, and then there's a metering zone on the screw. What does each of these things do? In the feed zone, you do not want to melt the plastic, okay, especially in the back part of the feed zone. Yeah, typically on a general purpose screw, which is a GP screw, you've got this portion is 50% of the screw, this is about 25%, and this is about 25%. Right, the outside diameter stays constant, but look at the inside diameter is constantly changing. So what happens? The plastic comes in here. When the plastic comes in here, now if you melt the plastic right here at the feed throat, right, what happens? Let me go to this, right? What happens if you melt the plastic right here in the feed throat? Then the plastic going to get stuck here, not going to be able to get the new plastic inside out here, right? The fresh plastic. So you just want to get the plastic here, do not want to melt the plastic. By the time the plastic comes to the back of or the front of the feed section or the back of the transition section, now these things are like, think of them like marshmallows, really soft and completely molten out here. Not completely molten, but they're very soft by the time they come in this area here. This is your feed zone. Then you take these marshmallows, and because there's a reduction in the diameter, the feed depth, right, or an increase in the diameter or the internal diameter here, what happens? Now you're squeezing those marshmallows and you're pushing all the air out of the system. Yeah, so look at these images that I've taken out here, right? It took me a long time to get these images. I had to pull the screw out like 5 times to get them this way. But you can see in the feed zone, the plastic is they're all stuck to each other. Pellets are stuck to each other. Why? Because of like the marshmallows out there, right? But you can see there's a lot of space. What is in between the space? That is basically in the space that is air in there, right? When it comes to the transition zone, this is where you now start to compress it. Yeah, as you start compressing this, you'll now see that there's still some amount of not unmelted plastic, but still some air in these areas. But by the time this plastic comes to the back of the metering zone or to the front of the transition zone, now you have squeezed out all the plastic, or you should have squeezed out all the plastic. Okay, so applying that back pressure, right? So I just say made it bigger for you guys to see out here. Applying that back pressure from the back over here, what it does is it helps you compress these these marshmallows pellets and push all that air back from into the hopper, right? And that does happen. Okay, it's not necessarily only air, by the way. It could be some of the volatiles that are in your plastic. Every plastic that comes to you to mold is not just neat plastic. It is always has got some chemicals added to it or some additives added to it. So it could happen that there are some low, and all these additives are low molecular weight additives like plasticizers and other other additives there. They're all basically low molecular weight additives which can burn easily. So what happens is as they start conveying because of the heat, they can start getting burned because of friction or the shear heat and so on. All those gases, all those volatiles, right now they start getting pushed out through the hopper. Okay. For some of y'all who have had experience, a lot of experience, you may have noticed that you're running plastic and you start seeing there's a lot of splay on the parts, etc. Or sometimes when you move the hopper back and we'll go look at the feed throat area where the plastic's coming in, you may see that there's some sort of residue there. Okay, some liquids and residues there. Yeah, what's happened there is basically the plastic as those additives they start burning. And they start getting squeezed out here. It basically starts to go back up through the hopper, and it starts to, because the feed throat is cold, they actually start to condense over there, and you get this problem. I have seen that problem with polycarbonate quite a bit. Okay, so processing of polycarbonate sometimes, depending on the grade, of course, is you have to be very careful. So anyway, so this back pressure that you put on this, right? This back pressure that you put now helps you squeeze that plastic pellets efficiently and effectively so that you can squeeze all the air out of there and you get a melt that is free of any volatiles. If you have volatiles, what happens? You end up with splay, right? So I just literally ran this part yesterday for my seminar and I had to do this this class today. And I said, let me get some fresh parts. So see, this is with back pressure. Yeah. And then when I took the back pressure out, so you can see the splay out here, the splay out here in this area of the part, right? So why is this coming? Is because that air did not get out of the melt stream. And therefore, again, applying back pressure is important for you to get rid of the splay on the parts. It's a cosmetic defect. If it comes onto the surface, it is splay. If this air stays inside the part, then it becomes a bubble or it becomes a void inside, right? Always the splay happens because of fountain flow. As the plastic flows through the cavities, you get this fountain flow effect and you get splay on the part. Yeah. So again, please do this. When you guys go back to the molding machines, please do this. Go take a dark part like this. I actually run a white part for my seminars, but I put some colorant in there yesterday. And take a dark part like this. Reduce your don't change anything, right? Don't change anything. In fact, leave your pack and holds also the same way. Reduce your back pressures by certain amounts and keep reducing the back pressures, and you'll start seeing that there's this splay on the parts. You do it for ABS, do it for, this is actually a HDPE, Alathon material, it's a HDPE material, right? So the second reason that we need to apply back pressure is because of to get rid of the splay or to get rid of the bubbles. Then we come to the third one, which is very important, right? So now remember the PVT diagram that I showed you. Plastic melt is compressible, and that's what happens in the injection molding machine. You're injecting the plastic and now reducing the volume. Reduction in volume is what? Is shrinkage, right? So you need to get consistent parts. What are we looking for? We're looking for consistencies. Yeah, there are three types of consistencies. There is a cavity to cavity consistency. There is a short to short consistency, and then there's a run-to-run consistency, right? So we are always looking for consistency, consistent dimensions. So what is consistent dimensions? That means we need consistent shrinkage. If you want consistent shrinkage, that means what? We need consistent amount of molecules inside the cavity, right? From shot to shot and run to run. What is consistent number of molecules? Means consistent shot weight. Yeah. What's the formula for weight? Weight is equal to volume multiplied by density. What is, for us, what is volume? Shot size to transfer, right? That is a volume. And then shot size to cushion, where we end up with. If your shot size to, if your cushion value, right, that's a total volume that you're going to inject. We want to find out if the volume, I mean, if the amount of plastic inside the cavity is constant. We know that shot size to transfer position, we are going to transfer into pack and hold in by position. So this volume is distance is constant, therefore volume is constant. And therefore now what is remaining? If you want to have the a consistent weight, you want to have consistent density, which is what? The melt density, right? The plastic melt density has to be constant, right? And therefore a consistent melt density is required for us. Again, plastic melt is compressible. That means what? If I put more and less pressure here, what's going to happen? The amount of plastic inside this is going to start changing in there. Therefore, again, you need to have amount of back pressure in there, right? That back pressure is need to make sure that that melt density stays consistent. Yeah. So what do you do in this case? If I want to have a consistent melt density, what should I do? So the answer is very simple, right? So all I came up with, and I'm just going to show Dave for yesterday's seminar information here, right? So this is the awesome software that I have for process development. So if you see this in the, let me open now so what did I do, right? I'll just show you this, right? Let me open the seminar mode. This is the seminar and melt preparation. And this is my April. So this is Dave for yesterday. We did this, right? The first thing you do, of course, is a screw rotation speed. I'll come back to this. All I do to come back to know if I've got consistent back pressure is I mold 10 short shots, right? I mold 10 short shots without any pack and hold pressures and I weigh them with the runners. So see, I set the back pressure at 250 psi. I molded 10 short shots. I've got the min and the max and I got the range. I went from 250 to 500 to 750 to 1000. And what happens? As I started adding more and more back pressure, see the range kept on decreasing. What is the range? The range is the difference between the max and the min. That is the range, right? So see, it became more consistent. At 250 psi, the range was 0.328 grams. At 500 psi, it was 0.076. At 750 psi, it reduced even more to 0.041. See, the more I pack it out, the more consistency I get from the from shot to shot in there, right? So that's what shows you. So it's very easy, right, to know. And but I'll come to this. If you go past a certain point, so I went above from 750, I went to 1000. What happened? The inconsistency or the consistency, it decreased. Right? It went to 0.076. By the way, this is extremely coincidental that 500 and 1000 are showing the same numbers. I never, it's just should have bought the lottery on that day, I think. But this is just a coincidence, but it will happen. I do see this, right? And you may also see this. What's happening here? The reason you get inconsistency after some time is because now you start, the plastic starts to slip, right? I'll come to that. But just look at this data, right? This is the one that shows you how to now set your back pressures for the molding machine. So what will I choose from this is the one that gives me the least amount of variation. So in this case, we chose a plastic pressure of a back pressure of 750 plastic PSI. Okay, this electric machine that I have here, it's a plastic PSI out there, right? So this is how you set your back pressures. Is it a lot of work? Think about it. It's like 30 shots, 40 shots, right? It's not a lot of work. I would say that you should go ahead and do it. Okay, and you may have to do it just once. By the way, you don't have to do it every time the mold comes back for validation, because this is all part of melt preparation studies. We are not first thing we have to do is to make sure the melt is consistent, right? That what we're getting is consistent, right? So you will have to do it only once. If you have to go modify the mold, you do something else to the mold, you need not do these studies again and again. Okay, I'll give another tip here at a later point, right? But I hope everybody understood the study. It's a very simple study. Out here is what we do. Also, just as an just for FYI, because we're talking about the melt preparation part of it, there's the back pressure. We also do a screw rotation study, right? So how do you optimize the screw rotation speeds? There are two sources for heat for generating melting the plastic. One is your barrel temperatures, right? Where you set the barrel temperatures, and the second one is the screw rotation speeds. As you start increasing the screw rotation speeds, so you can see I went from 4 inches per second to 7 inches per second to 10 inches per second. You'll see that what happened, the plastic temperature increased in here. Why is that? Because I'm giving more and more shear. Sometimes, like this one, it flattened out. So 7 and 10, they're almost the same. That means what? Initially, it was shear sensitive. After that, it's not shear sensitive at all. Okay. In fact, we started optimizing this, and we were using a screw rotation speed of 7. We said we leave it at 7, but at 7, the screw rotation time was about 6.4 seconds, and then we could still run a faster cycle. So then we went to 10 inches per second, reduced our screw rotation time, and we were able to get a faster cycle. So I do all that stuff hands-on here, by the way, in my classes, right? But again, this is part of the screw rotation speed, right? And why am I telling you this? Because there's another concept I'm going to tell you about screw rotation speed here very soon. Yeah. So going back to back pressure, this is how you set your back pressure values in there. Yeah. So the study is very simple. All you're going to do is you're going to come in here and mold 10 short shots at various back pressure values. Make sure when I say weigh and record the short shot weights, you must record all the parts and the run system, because that is your total shot that is being injected from the shot size to the transfer position. Okay, good. So this is how you set your back pressures based on a study that we have here. Okay, so if you look at this, we have got 3 reasons for that we need to use the back pressures correctly. First is for consistency during fill. How do you know it's consistent? Also start looking at your screw rotation times. Okay, if your screw rotation times are consistent, that is one thing that tells you you're recovering the plastic consistently. It does not mean that you have got to the air or if everything else is consistent, but your screw rotation time should be very consistent. If it's going all over the place, right? If it's like 10 seconds plus minus 2 seconds, then that's a lot of variation out there. Okay, so that's the first thing you look for on the history or the output page on the machine. And then second is you need to make sure that removes all the air during recovery. And then the third one is basically you compress it to get the same equal amount of consistent shot for the consistent amount of plastic for the next shot. Now, if I am molding a part and out here at 750 psi, I say that I have got least amount of variation, but I am now getting at 750 psi, I'm now getting, where did it go? Sorry, I think I went too fast. Now I'm getting splay. What do? Right? If you're getting splay at 750 psi, and if I increase the pressure now to 1000 psi, like over here, 1000 psi, and it goes away, then you must use 1000 psi. Okay, that is what I would use, right? It's still not, I mean, yes, there's a little bit of variation, but 0.4, what's the number here? Yeah, 0.076 is still not too bad, right? So you must therefore use a higher pressure if you have got, if you're getting splay problems over there. Then increasing back pressure increases melt temperature, right? A lot of people say that. Yes, right? Think of this car, right? If you floor it, what happens? The tires, they start turning in place, and basically what happens, they're burning the rubber at that point, and now the temperature goes up there, right? And that's exactly what happens is that if you go to a certain point beyond this over here, then now what happens is you're putting so much back pressure. I shouldn't say so much back pressure. You're putting enough back pressure there that now there's a lot of resistance for the screw to come back. Remember, there's nothing pulling the screw, right? It's always being pushed because of the plastic. But if you now put so much back pressure, you're compressing the melt, the screw is turning in place, and when the screw is turning in place, you start seeing an increase in the melt temperature. So you will see an increase in the melt temperature in this region, but you should not be seeing any melt temperature in this region. In this case, it is only the shear energy, or the shear from the screw, the turning screw, that is going to melt the plastic. Yeah, the turning of the plastic, like I showed you in that graph, the turning, the screw rotation is going to give you an increase in the temperature. But again, it's also conveying the plastic. But in this area here, now without changing a screw out rotation speeds and without changing the barrel temperatures, you will there definitely see an increase in the melt temperature. Okay, again, this is the only place I get rid of splay. Is that bad? No. If your melt temperature is within the recommendation numbers, then that's fine. As long as you stay within recommendations and you're not having any issues with consistency and you're not like maxing out machines. Yeah, let's say the max melt temperature is 550 and you're getting a melt temperature of 545, then you have to be very careful. Okay, but if your max is 550 and the melt temperature went from 500 to 510, absolutely fine. There's no problem with that, right? But yes, it does increase the melt temperature, increase back pressure, but that happens only in this area out here. Okay. Yeah, so melt temperature will increase there, and there's no melt temperature that will increase in this area here. Yeah. Decompression, it's not, I mean, it is related to back pressure, by the way. Okay, what is decompression? Is because I've now applied that back pressure here, right? I've now put 750 psi of back pressure here. When the mold opens, if it's a cold runner mold, if the mold opens, now there's this is completely empty out here, right? There's no sprue. So now it's literally going to, because the pressure is going to come out of the nozzle tip, right? And because it comes on nozzle tip, now you might freeze the nozzle over there, the plastic there, you're going to have shots and so on and so forth on the next shot out there. So what you do is that you have to linearly pull the screw back without rotation, so that you're just simply reducing the pressure inside in the barrel out here. And that is what is called as you're decompressing the melt. Use as little compression as you need. Okay, don't use too much. All you have to do is to make that pressure inside the barrel zero, so it doesn't drool out. Yeah. So again, that is related. Higher back pressure you use, the more decompression you're going to require. But again, it's not typically not more than on, let's say, a 35 millimeter screw or 60 millimeter, even up to 60 millimeter screw. You don't need to have a decompression of like 1 inch. It's literally maybe 2.25 inches to 0.35 to 0.4 inches, right? Again, even half an inch, I think is just too much. Okay. There's also some people say that if I've got too much decompression, I'm going to suck in air inside the barrel. That is totally impossible. Okay. If you're sucking in air from this region here, that means what? There's a leak, right? There's a leak. And if there's a leak, then during injection, plastic is going to come out. If the plastic is not coming out, there's no way, because plastic is being injected at extremely high pressures, right? So you're definitely going to leak plastic over here if there's a leak, right? So it's impossible for you to suck in air during suck back. Now, if you've got too much suck back, you will create a vacuum void in here. So when the mold opens, the part falls out, and if the plastic is still molten here, at that time, because of vacuum, the air can get sucked in. Okay, so that's a possibility. So again, just think of that. That's what it will typically happen in there. Okay, I think good, right? Again, please don't do this. I'll send you this really nice parameters. If you want, send me an email. Do connect with me. And again, thanks to Sodick for giving me this opportunity. I think I have worked with Sodick machines before. There's a customer of mine in Texas who has got only Sodick machines, and they're very happy with it. Right, they're very happy with it. I think for the shot controlling the shot is extremely important, right? So I'm a data-driven guy. I like data, right? All my processes are based on data, right? I will not, if you ask me, hey, what should I do to make a part bigger? I will not tell you the answer to that by saying, go change the cooling time, go change this. You have to do DOEs, you have to look at data. Sometimes cooling time makes no difference, right? And these machines, I'll tell you, I've looked at the data that for the quality that comes out of this, they're just fantastic. Okay, so again, thank you, everybody. I'm open to questions. If anybody has any questions, that's my contact information out there. Feel free to give me a call. That's actually my cell phone number. I don't mind you guys calling me on my cell phone, and that's my email address in there. Okay, excellent. Thank you.
Excellent. Thank you, Suhas, very much. We did have some questions already start coming in, and as Suhas mentioned, please send more questions. He's happy to answer anything you have right now. Maybe the first question here is just kind of high level for you, Suhas, but can they get a copy of the slides and the recording of this video? I know we're recording it, looking forward to making that.
Yes. Yeah, I will send out. Yeah, I will send out a PDF of some of the slides. Yeah, absolutely no problem at all. Yeah,
wonderful.
Yeah, if you guys teach your own seminars, send me some money.
So next question is if you could highlight maybe on hot runners and its influence on the PVT.
That so think of a hot runner system as a continuation of the mold, right? So really the effect you should always look at what is happening inside the cavities, right? So you've got a pressure sensor in there. With hot runner systems, what happens is the pressure that you apply behind the screw, all of it is still used to compress the melt inside the hot runner system, and then inject the plastic inside the cavity. It's like a big cushion out there. So really, the PVT is still, so that if I'm understanding your question correctly, if I've got a part that I'm molding with a cold runner, and you have got a part, the same part is now being molded with a hot runner system, what influence does that have on the pressure inside the cavity? Definitely, you know, if you have got a cold runner system, you're going to end up with lower pressures inside the cavity because of fountain flow, and you're going to have a lower pressure, and the PVT is going to look completely different, or your pressure graph is going to look different when you if you have the same molding process, that is, when you compared to what you have in a hot runner system. Yeah, but again, you must try to match the PVT or the pressure graph from an RJG sensor or whatever the sensor in both these things, right? But it's really not a whole lot different between the two materials. I mean, the two systems, if I'm going to try to make the same part. And if I did not understand your question properly, whoever asked the question, please contact me and we can discuss it further.
Great. Next question for you here. As we tend to run the screw speed study, what is the back pressure set at?
At that, so whenever you run any of these studies, right? So let's say they start off with a viscosity study, you have to still set a pack and hold pressure. Well, not really, but you still have to have a cooling time. You still have a melt temperature, right? So when you're doing a screw speed study, start off with with your experience, right? Start off with about, I would say, about 600 to 700 plastic psi. You can optimize that later. Okay. Well, after you do the back pressure study, right, you'll see what the range is, but start off at that about 600, 500 to say 700 psi of back pressures.
Wonderful. And would that be the recommended back pressure for outside of the studies as well? I guess that's kind of a follow-up question maybe that you have answered. So let's move on to the next one, Suhas.
Yeah.
Next question, do you see varying optimal back pressures at different barrel profiles, temperatures, low, medium, or high?
So ultimately, if you do the study, you'll change the shot, you'll change the part weights will change, but the profile of the back pressure will stay the same regardless of where you run your study. Same thing with viscosity study, right? People ask me, where should I run the viscosity study? People say, when I ask the question in the class, okay, so what do you guys think? Where should I run my viscosity study? They say in the center of the profile. Really doesn't matter. The profile will stay the same where you go with the temperature, right? You're interested in the lowest, the profile, and you're interested in the lowest variation. And that you will get whether you run it at a high temperature, medium temperature, or low temperatures.
Excellent. Here's a question directed towards the Sodick machine, Suhas. Are there any back pressure recommendations suggested for the two-stage units versus a reciprocating screw?
So just ask the question again. I think so there is I mean, you guys have 2 units there, yes, but so is it in which, so ask the question again, maybe explain a little bit more better for me.
Sure. The question reads, any back pressure recommendation suggested for the Sodick two-stage units versus a reciprocating screw?
I do not know if this company has done back pressure studies and what the data looks like, but I would say if you have got a screw rotation, rotating screw, then absolutely you must do it this way. I have not personally done a study on the plunger type machines to see what it is, but it would be a good thing to do. In fact, the person who asked the question, if you guys can follow these guidelines and see what you get, and we can discuss it at some point. But I've not personally done that study on the Sodick machines. I worked on them, but not done. I mean, it's troubleshooting, but not the studies.
Yeah, and just to add to that, feel free to reach out to us, Weston or myself, and we can talk you guys through that. We didn't really want to derail this conversation with specifics on our injection unit, but we do have plenty of information regarding that. We can talk offline.
Great. Thank you, Bennett. Way to jump in there, man. And, excuse me. I guess let's move here. Is the back pressure resin dependent or machine dependent? Irrespective of the machine, does the back pressure have to be within a range?
Yeah. So that's why I said that, I'll bring up a point, and actually is that, see, ultimately, if you start collecting the data, you'll notice that for a given resin, regardless, that's why you should always go in absolutes, right? You always go in plastic pressures, you should always go in actual melt temperatures, and you should always go in screw rotation, the circumferential screw rotation speeds, right? So when you go from machine to machine, you're talking apples to apples. You'll find that for a given resin, typically that graph looks very much similar in those areas. So you can do 5 of this on a given, for let's say for an allothon. So when I do my studies here, I always get the same thing. Right? Of course, I shouldn't say that because I have the same machine, but you will end up getting similar results. And let's say after doing 5 of them, you'll say that's it, right? For this resin, we must always set the back pressure values to about 750. If you get splay, then increase it to 1000 psi. So after 5 of these things, you could probably stop doing these studies for every single mold out there. Yeah. So it should not be machine dependent, and it should not be. It will be resin dependent. That means you go from ABS, you go to polyethylene, it will be resin dependent, but for a given resin, it should be completely machine independent.
Wonderful, wonderful. Is it effective to set multiple back pressure settings if available, or should a single back pressure setting be enough?
Single back pressure setting. I don't see any reason to have 2 back pressure values ever. I've never used it, right? I've never needed. I mean, I think of the theory of back pressure, right? Why would you? There's no need to have back pressure settings profiles.
Great. If you don't have the TDS, do you have any recommendation that we could use as a baseline?
Don't have what? TDS?
TDS, yeah.
What's TDS? Sorry.
Yeah, maybe our listener attending that asked that question.
The technical data sheet. Technical data sheet, probably.
Okay.
Yeah. Yeah. If you don't have the TDS, okay. I mean, I think that's what TDS is saying, technical data sheet.
Yeah.
Recommendation, again, no. If you don't have a TDS, that's good actually, because I don't agree with those values, you know. So it's actually good that you don't have a TDS. I think you should just do a study like this. But start off, a good number again is like 650 or 700 PSI, right, in that range. Okay, plastic PSI. That's a good starting point. And then do a study there. Yeah. See, I really don't, there's other than melt temperatures and mold temperatures and drying temperatures, let's say, the rest of the processing information that they give on the data sheets, I don't trust them. In fact, like I said, I've done some studies and I've done some R&D, spent my own money to do some R&D on venting and all that stuff, right? So that is what I always look for. So in one way, it's good that you don't have the technical data sheet.
Great. A few more just kind of trickling in here, Suhas, but one is asked, and I'm not sure if quite what this question's about, but it said, I missed yesterday's presentations. Can I get the video from Suhas? So I'm not sure if, if there's another one that someone was looking to see from you, or we'll have our video will be available for him to rewatch. If that's what you're asking.
It's probably the last one that I did, which is also on my website. Actually, I've got I've got a YouTube channel also, where you can hear the DOE presentation that I did for Sodick last time. Okay, so you guys can do on my YouTube channel. I'm starting to put a few videos there. Yeah. And also to let you all know that I'm also starting all my classes. I'm recording them online, so you'll also get some online class at some point.
Excellent. Great. Maybe give just a few more minutes here for any last questions before we wrap up. And then we'll let Suhas go. I want to take a couple minutes here while we're doing that to say thank you for joining us again, Suhas. It's great. As always, very informational. Really appreciate your time. So
always a pleasure. Always a pleasure. And I hope to, for those of us who are still online, I hope that I can travel, and we're planning to do some talks and stuff like that at different locations. And so send me an email, so I'll put you on my email blast. I always send out some information, technical information on my email blast. It's not simply buy my software or buy my services. I'm very passionate about this. So send me an email, I'll put you on the email list, and you guys can probably come and listen to me at some location also in the near future. Yeah. And so again, thank you for all those who attended. I hope you guys are all enjoyed the class. And that's it.
Seems as soon as we say it's the last chance to get questions in, they come flying in here, Suhas. So I have a few more for you. And I did have one attendee say that they had directed a question to you. I didn't notice it come through, so you might want to see if it's on your screen. But
oh yeah. Wow, sorry, there's a lot of questions here. Oh my God.
Okay.
Oh.
And we can, Weston, if we need to, we can answer things separately, or maybe Suhas can.
Yeah.
I don't see a private question to me.
Okay. Then let me finish these questions up, and the
only private I have is that I'm unable to open the microphone for conversations, but that's not for you guys.
Yeah. No. Okay. The first question here that came in after that is, will this need to be done for different material lots?
No, I don't believe so. That should not be that much of a variation from lot to lot variations. No. Right. Lot to lot variations, you start seeing viscosity graphs, but in my opinion, absolutely not. You don't need to do it.
Excellent. Can you give the audience again your your YouTube channel name?
Just search for FimmTech. The YouTube channel, just search for FimmTech.
Excellent.
There's a few videos there, but I'm going to be putting more and more, so just keep a watch on that. Yes.
Okay. Do you find that you have to run back pressure below optimal setting for glass filled materials, you know, to prevent breaking the glass fibers down?
That is actually a fantastic question. Yes, yes. You can do these studies, but if you start seeing at the lowest variation, you start seeing that you're having issues with the glass fibers breaking down. Of course, you'll only notice that when you do testing of the product. Then yes, absolutely, you must reduce the back pressure and just deal with the variation in the shot to shot. In there, remember this: there are 11 plus 2, right? So even if you reduce your back pressure, you see that variation. That is not the final thing. We still have pack and hold that can still pack out the part and give you the consistency, right? Something is going to compensate for that, right? So don't worry about it. Set the back pressures where you need to, not really where where is like the lowest point. That's a great question. Yes.
Excellent. How can we get our star line to choose the best decompression size?
How can we get what? Sorry?
Get our star line to choose the best decompressor size.
Star line. I don't know what star line means, but I'm just going to assume that how do you set the decompression? Well, set the decompression. Let's say I've got a 30 millimeter or 35 millimeter screw. Set the decompression to 0.2 or 0.25 inches first. Do you see drooling? Yes, I do see drooling. Okay, so I go to 0.3, right? Use the minimum decompression that you need. That's it. That is a rule for that, right? So that you don't get frozen nozzle tips. You don't get drooling taking place. And of course, always make sure that you're using the right nozzle tip. If you're running nylon, you must use a nylon nozzle tip. But that's how you set your back pressure. That's why I don't even consider decompression my 11 plus 2 parameters.
Excellent.
Yeah.
And then is there a seminar coming up for you, Suhas, on scientific injection molding?
Yes, I have started on. I mean, I've started in-house now because things are opening up. In fact, I've got one in May. The May one is full, but I'll have one towards the end of May, another one, and then in June, they'll always be there. So please sign up. Yes. We're going to have it in-house here, and I'm also doing some online. So whoever is interested, please let me know.
Wonderful. Great. Thank you, Suhas.
Yeah.
Again, on behalf of Sodick, myself, Bennett, Len, and our team, thank you for jumping in here and doing a second presentation. And,
Excellent. Yeah, sure. And again, if I think someone said that they sent me in a private chat or something that way, send me an email. I'll be happy to answer your questions. So thank you again to everybody.
Great. Thanks, everybody. We will be back with Sodick and Friends on the 19th of May. Another great presentation coming up then. So we look forward to everybody joining again. Have a great rest of your day. Thank you.
Thanks to us. Thank you, Weston.
Yeah. Take care, guys. Bye.
Bye, guys.
Take care, everybody.